Welcome back, students, to the third part of our discussions on the lesson Work, Energy and Power. In the previous session, we had discussed in full detail about energy. What is energy? What are the different forms of energy? We had studied about kinetic energy in full detail, and then we had understood the concept of work energy theorem. Today, we will be discussing some more concepts related to energy. And the topic of discussions for today would be potential energy and law of conservation of energy. Prior to that, let's quickly recapitulate what is energy. The ability to work or cause change is called energy. When an object or organism does work on another object, some of its energy is transferred to that object. So we may think of work as the transfer of energy. There are two types of energy, kinetic and potential, about which we have studied in the syllabus of class 11. Already kinetic energy has been discussed. So we'll be discussing about potential energy today. Potential energy. The potential energy of a body is defined as the energy possessed by virtue of its position or configuration in some field. Thus, potential energy is the energy that can be associated with the configuration or arrangement of a system of objects that exert forces on one another. Obviously, if configuration of the system changes, then its potential energy changes. You can see right now on your screens few examples of potential energy, like stretching a rubber band stores energy, water at the top of a waterfall stores energy, yo-yo held in your hand stores energy because of position, drawing a bow stores energy because of position. So we may categorize potential energy into different types, and two important types of potential energy are gravitational potential energy and elastic potential energy. One more form is there, chemical potential energy, but we shall study only about the first two. So after going through all the examples, one thing that we have understood is that potential energy is that form of energy that is stored and held in readiness. So if you analyze the examples, when we wind the spring of a watch, potential energy is stored in the spring on account of configuration of the turns of the spring. As the spring unwinds, it works to move the hands of the watch. Thus, the wound spring has the potential to do the work. Similarly, when a spring is compressed or stretched, work done in compressing or stretching the spring is stored in the spring in the form of potential energy. Again, when a stretched bow is released, the arrow goes forward with a large velocity on account of potential energy of the stretched bow. So we have understood that an object may store energy by virtue of its position. Energy that is stored and held in readiness is called potential energy, because in the stored state it has the potential for doing work. Gravitational potential energy. Gravitational potential energy of a body is the energy possessed by the body by virtue of its position above the surface of the earth. The SI unit for this energy is joule. Now let us consider one example. For example, in the 1996 Olympics, when Andrew lifted the record-breaking weights above his head, he increased the separation between the weights and earth. The work his force did changed the configuration and hence changed the gravitational potential energy of the weights earth system. In fact, the amount of work done in carrying the body from surface of earth to its present position against the gravitational force of earth is stored in the body in the form of its gravitational potential energy. When the body is allowed to fall from that position, it can do the amount of work equal to its gravitational potential energy. For example, gravitational potential energy of water stored to great heights in dams is used to run turbines and produce electric energy at hydroelectric power stations. Now let us calculate the formula for gravitational potential energy. For this, let us consider the following situation. Suppose a ball has to be taken to this particular height. Let this height be equal to h. Now, to calculate gravitational potential energy, we have assumed that we have an object of mass m. The acceleration due to gravity is given by small g, and h is the height through which the body is raised. If we assume that height h is not too large and the value of small g is practically constant, that is, acceleration due to gravity is practically constant, then the force applied just to overcome gravitational attraction we denote it with F, then the force applied just to overcome gravitational attraction is given by F equal to m into g. Now, as the distance moved is in the direction of the force applied, therefore work done is equal to force into displacement, that is F into h. Now, if we substitute the value of F, we get mgh. So work done comes out to be equal to mgh. Hence, gravitational potential energy of the body is equal to the work done, and that is equal to mgh, as you can see in the previous page also. At the surface of the earth, where h is equal to 0, gravitational potential energy would always be equal to 0. Obviously, gravitational potential energy varies directly as the mass of the body and also directly as the height of the body above the surface of the earth. Now, here it should be clearly understood that gravitational potential energy associated with the particle earth system depends only on the vertical position of the particle relative to the reference position, not on the horizontal position. One thing I would also like to mention at this point, that potential energy is defined only for conservative forces. It does not exist for non-conservative forces. Potential energy depends upon frame of reference. It may be positive or negative. Now, there is a convention. By convention, in a conservative field, potential energy is equal to negative of work done in moving a body from some reference position to a given position. The formula potential energy equal to mgh is the gravitational potential energy of the earth body system. The height is always taken above some reference level, as you can see in the diagram, which is defined in the given problem. If reference level is taken as surface of earth, then variation of gravitational potential energy with the height is obviously linear in nature. Potential energy, or rather gravitational potential energy of a body, is said to be positive when work is done by the body in returning to its reference position. Similarly, gravitational potential energy of the body is said to be negative when work is done on the body to bring it back to the reference position. Coming to the next form of potential energy, that is potential energy of a spring. Springs can be of many types. We may be having a helical spring or a spiral spring. Usually, we assume that the springs are massless. Therefore, restoring elastic force in a spring is same everywhere. To produce compression or extension in a spring, two equal and opposite forces are to be applied on the spring. In equilibrium, restoring force developed due to elasticity of the spring is equal to either force and is always opposite to the applied force. A definite amount of work has to be done against the restoring force, both in compressing or in stretching the spring. This work done is stored in the spring in the form of elastic potential energy of the spring. So, as you can see in the diagram given alongside, in one case we are compressing it and the other case we are stretching it. So, as I was telling you, that a definite amount of work has to be done against the restoring force, both in compressing or in stretching the spring. This work done is stored in the form of elastic potential energy of the spring. Thus, potential energy of a spring is the energy associated with the state of compression or expansion of an elastic spring. In order to calculate it, consider an elastic spring OA of negligible mass. The end O of the spring is fixed to a rigid support and a body of mass M is attached to the free end A. Let the spring be oriented along x-axis and the body of mass M lie on a perfectly frictionless horizontal table, as you can see in the figure. I am talking about the first figure, that is A. Now the position of the body A when spring is unstretched is chosen as the origin. Now when the spring is compressed or elongated, as you can see in the next two figures, when the spring is compressed or elongated, it tends to recover its original length on account of elasticity. Now the force trying to bring back the spring, or the force trying to bring the spring back to its original configuration, is called restoring force. Now for a small stretch or compression, spring obeys Hooke's law. That is, for a spring, restoring force is directly proportional to the stretch or compression. We may write down F to be directly proportional to X. Now a negative sign is put in front of F because the restoring force always acts opposite to the applied force, as you can see in that diagram. Just see the second diagram. F is actually restoring force. Suppose when the block M is pulled so that the spring gets elongated, the restoring force will always try to bring the spring back to its original configuration. So obviously it has to act opposite to the applied force, in a direction opposite to the applied force. So the displacement of the spring, the displacement or the change in length of the spring, in this case elongation, takes place in a direction opposite to the restoring force. So that's why, as per Hooke's law, we can write down minus F to be proportional to X. And as we all know that if you want to remove this proportionality sign and put an equal to sign, then we have to introduce a constant. So we can write down minus F to be equal to K into X, where K is a constant of the spring and is called spring constant. Now from this equation we can also understand that greater the stretch or compression, greater will be the restoring force. So we can now see that the force constant or what is also known as the spring constant K is equal to minus F by X. Therefore, force constant of a spring is equal to slope of force versus stretch curve. If we plot a curve for force and the stretch or compression X, we find that it is a straight line because F is proportional to X. So force constant of a spring is equal to slope of the force versus stretch curve. Its unit is Newton per meter and dimension is m t to the power minus 2. Greater the force constant of a spring, smaller will be the stretch or compression of the spring for a given force. Therefore, a spring with greater force constant is said to be stiffer. The reverse is also true. Now, if x is equal to 1, F will be equal to minus k into 1, which implies that k is equal to minus of F. Therefore, force constant of a spring is numerically equal to the force required to produce unit displacement, which could be either compression or stretch in the spring. The value of k depends on length of spring L, radius of the spring R, radius and nature of material of the spring wire. So we can write down that k is inversely proportional to length. And if a graph is plotted, between the force constant and the length of the spring L, then the graph is somewhat like this. That is, smaller the length of the spring, greater will be the force constant. The negative sign in this equation indicates that restoring force is directed always towards the equilibrium position. As you can see in this diagram. Now, let the body be displaced further through an infinitesimally small distance dx against the restoring force. Suppose if we follow this diagram, we are giving a small displacement dx against the restoring force. So therefore, small amount of work done in increasing the length of the spring by dx. As we all know that work done is force into displacement. So small amount of work done dw will be equal to minus f into dx. And that is equal to kx dx as per Hooke's law. Therefore, total work done in giving displacement x to the body can be obtained by integrating the above equation. So we can write w to be equal to integral x equal to 0 to x equal to x k x dx, and on integrating we get k to be the constant. It is taken out of the integral, so on integrating we get x square by 2 using the standard integral formula, and obviously it is on the limits x and 0 to x. So on putting the limits we get work done to be equal to half kx square. This work done is stored in the spring as potential energy of the spring. So therefore the potential energy of the spring after this displacement, as you can see in this picture, potential energy of the spring at B, so that will be equal to half kx square. Now if we plot a graph showing the variation of potential energy with distance, then the graph will be like this. If we want to show the variation of potential energy and kinetic energy for change in distance, then We can show it in this manner. As we have just seen the graph for potential energy, so with dotted lines I am showing the graph for potential energy, and for kinetic energy it would be like this. So the total energy always remains constant. Coming to the next topic of discussion, the law of conservation of energy, or the principle of conservation of energy. According to this principle, the sum total of energy of all kinds in an isolated system remains constant at all times. This means that energy can neither be created nor be destroyed. Energy can only be changed from one form to another. The amount of energy appearing in one form is always equal to the amount of energy disappearing in some other form. The total energy thus remains constant provided at all points we measure the amount of energy present in each form, including mass, which too is a form of energy. Now, let us understand this principle by the conservation of mechanical energy. Let us consider an object of mass O, of mass m, falling freely under gravity. So we will be considering three positions A, B and C. So the total height is given by h from the ground. Let the distance between A and B be x. Obviously B to C will be h minus x. M is the mass of the body held at a height h above the ground. So as the body is at rest, so at A, kinetic energy is equal to 0 and potential energy is equal to mgh. Therefore, total energy, if I represent it by E1, then it should be equal to kinetic energy plus potential energy. So that will be equal to 0 plus mgh, and that is equal to mgh. Let us mark it as equation 1. Now let the body be allowed to fall freely under gravity. During free fall, let the body cross any point B with a velocity v1, where AB is equal to x. So now we know that v square is equal to u square plus 2as. Substituting the values, the velocity at point B is v1, so we can write down v1 square. The initial velocity was 0 and the body has fallen through a distance x. So we get v1 square equal to 2gx. Therefore, kinetic energy at B is half m v1 square. It is equal to half m into 2gx. 2 and 2 gets cancelled and you get mgx. What about potential energy? Potential energy is equal to mg, and now check the height of that object from the ground. It is h minus x. So we can write down mg h minus x. Let us calculate the total energy. If I represent it by E2, then it should be equal to again kinetic energy plus potential energy, and that is equal to mgx plus mg h minus x. On solving, we get mgx, the first term, and let us solve the bracket part now. So it gives us mgh minus mgx, and cancel these two, and you are again left with mgh. Let us mark it as equation number 2. Now, when the body is again allowed to fall freely under gravity and it strikes the ground C with a velocity v, let the velocity of the body at C be equal to v. Then we may write down again using this equation v square, initial velocity is 0 plus 2g, and now it has fallen through the entire height, so 2gh, which gives us v square equal to 2gh. Therefore, kinetic energy at this point will be equal to half mv square, that is half m into 2gh. You can cancel and you get mgh. Potential energy of the body, that will be equal to mg, and now the height is 0, so that will give you 0. So total energy, that is equal to kinetic energy plus potential energy, that is equal to mgh plus 0, and again you get mgh. Mark it as equation number 3. So from equation number 1, equation number 2, and equation number 3, we find that E1 is equal to E2 is equal to E3, and that is equal to mgh. That is, total energy of the body during free fall remains constant at all positions. The form of energy, however, keeps on changing. At A, energy is entirely potential energy, and at C, it is entirely kinetic. In between A and C, energy is partially potential and partially kinetic. Thus, in an isolated system where only conservative forces cause energy changes, the kinetic energy and potential energy can change, but the mechanical energy of the system, which is a sum of kinetic and potential, cannot change. Now, this law has been found to be valid in every situation. No violation whatsoever of this law has ever been observed. Hence, what remains constant in our universe is the energy. One more application of the law of conservation of energy might be taken in the case of the vibrations of a simple pendulum. So if you consider this example, A is the normal position of rest of a simple pendulum. When the bob of the pendulum is displaced to B through a height h, suppose it is given potential energy equal to mgh, where m is the mass of the bob. On releasing the bob at B, it moves towards A. Potential energy of the bob is being converted into kinetic energy. On reaching A, the entire potential energy has been converted into kinetic energy. The bob therefore cannot stop at A. So, account of inertia, it overshoots the position A and reaches C at the same height h above A. The entire kinetic energy of the bob at A is converted into potential energy at C. The whole process is repeated and the pendulum vibrates about the equilibrium position A. At extreme positions B and C, the bob is momentarily at rest, therefore its kinetic energy is equal to 0. The entire energy at B and C is potential energy. At A, there is no height and hence no potential energy. The entire energy at A is kinetic energy. So in this manner, we can understand the law of conservation of energy. We shall end our discussion for today. At this point, we shall be discussing about a very important topic, collisions, in our next session. Thank you.